So we're going to continue to add to a whole long list of tests, in addition to the integral test, geometric series test, telescoping series. We're going to add in the comparison test and the limit comparison test. Now, the book calls it the comparison test. I call it the direct comparison test. That's just me. That's what you're going to hear me refer to things as. But, you know, call it whatever you like. Your job is to know what it means and what it says. So it's a nice, clever way to help test for convergence or divergence of a series. If you know a series that looks similar to one that you're working with, then maybe it'll work for you. So how does it work? Well, let's assume that B is a convergent series, or that this first series is a convergent series. And why is that not working? Let's see. Yeah, here we go. So if this is a convergent series and B sub n is bigger than A sub n, well, we already know that this sums up to something finite. Assuming that we have positive terms for all this, if this sum is finite, then this has to be finite. And another way of saying that this sums up to something finite is saying that it's convergent. So if you can find a series that you know is convergent, that's bigger than the one you're looking at, then you can say, all right, well, by comparison, then the series for A has to converge. Now it has to be in the right direction. B has to be bigger than, the series for B has to be bigger than the series for A, and B has to be convergent. Now another thing that could be the case is you could have B as a divergent series. Now what does that mean? That means that it sums up to something positive, or excuse me, sums up to infinity. It doesn't converge, it's not finite. And if B is on the smaller end of things, and somehow or another A is on the larger end, but if B is on the smaller end of things, then the fact that B sub n diverges means that A sub n has to be divergent. So it takes a little bit of care to use the direct comparison test. It's not my favorite, but it can be quick and dirty. And let's do some examples to explore that. So let's take a look here. We'll reset and go back down to example A here. Let's take a look at this sum. The sum from n equals 1 to infinity of 5 over 7n squared plus 3n plus 4. Wow, that's a big mess. But when you're looking at these terms, especially when you start thinking about larger and larger values of n, these lower order terms really aren't going to matter too much. When you start looking at terms like a million, when you square a million, you get a trillion. So this would be 7 trillion. This would only be, well, 3 million. So what happens to these terms doesn't matter in the long run. And so what you could think of is, let's take a look at, we'll call it B sub n equals 5 over 7n squared. And why did I choose that? Well, because really only the terms that matter, the term that matter is this term there in the denominator. And this allows me an easy comparison to my A sub n. So we'll call that A sub n. A sub n is 5 over 7n squared plus 3n plus 4. Since we're dealing with positive values of n, this has to have a larger denominator. Now, if it has a larger denominator, what kind of inequality can I write between these two? Which one's bigger? Am I going to write less than or greater than? Less than or greater than?
Less than. B is less than A.
B is less than A. Is that right? No.
B is greater because
B is greater than.
let's,
Because this is a bigger number. I mean, let's just give ourselves a couple easy examples. 5 over 7 times. If I put in like a 3 here, that'd be 5 over 21. If I put in a 3 here, I'd have 5 over, let's see, 34. Which one's bigger? Well, the one with the smaller denominator, right? So the inequality would have to run this way. Okay, so how does that help me? Well, that helps me because I can think of something with this series. In fact, what do I know about that series? The sum from, let's do k equals 1 to infinity, just for giggles, 5 over 7k squared. The 5 and the 7 are constants, so I can bring that out here.
It's a P series?
Yeah, perfect. That's a convergent P series. And because this converges, then this converges by the comparison test. This is smaller than this series. This converges, this has to be finite. And that's it. Yay. So what I'd like to see you write is, and you don't have to write the little dots here, you could write therefore, I'm just being lazy. Therefore, the series and I'm not going to write the limits, converges by the direct comparison test. That's all there is to it. So kind of nice in this example that we got to review P series along with that. So worked out good. Any questions on this first one? Let's do a couple more, and then we'll take a break before we do the limit comparison test. It'll be our last test for the day. So I'm on pace for an average day. Usually I go through about 16 pieces of paper. So on track there. Example B. Let's take a look at the series 1 to infinity of the ln of 5k over 4k. All right, well, let me notice one thing for you. You know, all things aside, in the denominator, I've got a first power, which makes me start thinking of P series. Now, if I have something with just a first power in the denominator, what is your P series stuff going to tell you? Is that going to converge or diverge? Ignoring everything else. It's going to diverge, right? So you might start thinking that this series is going to diverge. If we want to prove divergence, then according to our little direct comparison test, where did it go? Oh, there it is. According to our direct comparison test, I need to find something smaller than our series. So I need to find something that's less than log 5k over 4k and show that that smaller series is going to diverge so that the bigger series has to diverge. And like I said, it's a little tricky to be careful with the direction this thing has to run. To that end, let me note that ln of 5k is bigger than 1 for any value of k greater than 1, k greater than 1. So it's bigger than 1. Why did I choose 1? Because if I can replace this with a 1, then I have a much simpler series. So what I'm going to do is I'm going to choose b sub n equal 1 over 4k. And this is going to be my a sub n. Now let's compare b sub n versus a sub n. A sub n is ln of 5k. Actually, I should put ln of 5n, I suppose. That should probably be consistent. Has to be ln or a sub k. A sub k, I'm just so used to using n's, I'm sorry. So I'm making everything k's because I chose to use the sum from k equals 1 to infinity. So this is a sub k and this is going to be b sub k. I'm sorry. I hope I didn't confuse you too much. All right, so here's my general term here. And then 1 over 4k is b sub k. How do these things compare?
A sub k is greater.
Yes, a sub k is greater.
How is it greater?
Well, the denominators are the same, right?
Right.
So the bigger one's going to be whatever numerator is bigger. And ln of 5k is going to be bigger than 1. I mean, you just take the natural log of 5 on your calculator. All right, let's just do that. ln of 5 should be 1 point something. There you go, 1.609. The next term you put in here, k equals 2, is going to be ln of 10. And these numbers are just going to keep on getting bigger. So the natural log here is going to be bigger than 1 for all values of k. Does that help out? All right. Now, let's see what this is going to help us set up then. So if I look at this series, the sum from k equals 1 to infinity of ln of 5k over 4k, that has to be bigger than this sum, k equals 1 to infinity of 1 over 4k. Well, I could rewrite that as 1/4 the sum from k equals 1 to infinity of 1 over k. What do I know about that? Someone help me out?
It diverges.
P equals 1 here. Does a P series with P equal 1 diverge or converge?
Diverge.
Diverges, good. Now, if it diverges, essentially that means this is infinite. And if this is infinite and this is smaller than this, what's that telling me about this series? Can this converge? Can this be finite?
No.
No. So therefore, the series ln of 5k over 4k diverges by the direct comparison test. Whew. Awesome. Okay. One last example, and then we'll take our last break. Are we okay with example B here? Okay, let's take a look at the sum from, I'm using k again, darn it. K equals 1 to infinity of 1 over k cubed plus 5. Now, as you look at these series, you know, a lot of these, I mean, I can just look at these and say, oh yeah, it's going to converge, that's going to diverge, etc. But it's because I've trained myself not to look at small numbers like this. And when you're putting in a number like 1,000, 1,000 cubed is a billion. No one's going to miss that 5 when you're dealing with a number like a billion in the denominator. So I've gotten used to thinking of things like this, 1 over k cubed. And that's handy in this case, because what do you know about the series sum from k equals 1 to infinity of 1 over k cubed?
It converges.
Yeah, it converges. It's a convergent p series. P equals 3. P equals 3 converges. Thank you. So if it converges, well, maybe I can use that to help determine the convergence or divergence of this one. There's something fortunate here. You're adding 5 to that k cubed term in the denominator. That makes the denominator bigger, and you're dividing 1 by a bigger number. That means this term, our a sub n, or a sub k is smaller than b sub k. So that's cool. So that means the sum from k equals 1 to infinity of 1 over k cubed plus 5 is less than, you can put less than or equal to you want. It's actually going to be strictly less than the sum from k equals 1 to infinity of 1 over k cubed, which converges. We know this is finite. So therefore, by the direct comparison test, and I'm getting lazy here, the direct comparison test, this sum converges. But we were lucky in this one. We were lucky in this one because I had a sum here in the denominator. And when I got rid of that plus 5, I got something that was bigger and allowed me to converge or prove convergence by the direct comparison test. So the question would then be, this would be a question answered in the next video. Shameless plug for my next video. What if I had something like this? 1 over k cubed minus 5. I can't just easily get rid of that -5 and use the direct comparison test anymore, because all of a sudden, if you wanted to use direct comparison test with 1 over k cubed, that's not going to work anymore. You know, it's like, well, wait a minute. I mean, that's the natural thing to look at, but it doesn't work anymore. Because this would actually be, let's see which way it would be in the quality run now. Yeah, it would run this way. Sum from k equals 1 to infinity, like that. Now, if this is finite, we don't know if this is finite or not. We just know that this is finite. It says nothing about this, and that's actually one of the problems in your WebAssign homework, is saying something to the effect that, all right, well, if this one's finite, do we know anything about this? And the answer is no, we don't. Just because this is finite, this can be finite or infinite. Don't know. So let's solve that mystery in the next video.